Hello everyone, welcome back to this channel. Let's continue intermediate machine learning. As of now, we have completed up to cross validation. Okay, now we are going to understand about XGBoost. Before this, I will give you a small idea about XGBoost. Okay, whenever you have used any model, maybe linear regression, maybe logistic regression, maybe SVM, maybe decision trees, you have used a single model. But there is a technique called ensemble where you use multiple models together. Okay, it's like taking advice from multiple people so that you can have better idea. That is what is the main crux of ensemble techniques, and it is of many types. You may have heard this term voting, hard voting, soft voting, bagging. Bagging I will discuss. You heard about boosting, stacking, right? We will not go in depth, but we will have just a basic idea about the difference between bagging and boosting techniques. Okay, let's say you have a big data set. Okay, now in case of bagging, what is the method? You are using multiple models. So you have model 1, you have model 2, you have model 3, you have model 4, and all the models are trained parallelly. Okay, remember this term. All are trained parallelly at the same time. Okay, so first you are sampling a dataset from here, maybe dataset 1. Okay, sampled datasets. Same way sample datasets D2 with replacement. Same way dataset D3, dataset D4. You can use as many as you want. I have taken 4. Okay, so once you have trained this model, you have calculated the accuracy, and you have got your output from M1, from M2, from M3, M4. Once you get outputs from all of them, you are calculating your final output. Okay, so you understand the difference between bagging techniques and the traditional algorithms. Here you are using a single model, but here you are using multiple models, and you are creating different samples of dataset. You are training them, and then you are calculating the final output. Okay, this technique is known as bagging, and it is considered that it is better than any particular traditional machine learning algorithms, right? Now, what is boosting then? What is the difference between bagging and boosting? In case of boosting, you have a dataset, and you are taking your first model M1. So you are passing all the features to M1. Now your M1 has predicted something, so it has some errors, or we can say some residuals, the difference between the actual output and the predicted output. Okay, now what you are doing? You have taken your second model M2. So now you have the features and you have the errors. Okay, so you are passing the features plus the residuals, the mistakes done by the first model, so that M2 understand what to do, and M2 is generating output, and obviously some errors. Now you have the same features, so you have features, sorry, and you have the errors from M2, right? And you are passing it to third model M3. Same way, output generated, errors are calculated, again you are sending errors and features to M4. Okay, now see what is the difference between bagging and boosting. Here also you are using 4 models. I'm so sorry. Here also you are using 4 models, and here also you are using 4 models. But here all the models have no connection in between, and they are trained parallelly. But in case of boosting, see, all the models are trained one after another. So it is trained sequentially. Okay. Okay. So you get my point. Here models are trained parallelly and no model is connected to each other. And here all the models are trained sequentially. Fine. Now boosting is of many types, like gradient boosting, adder boost. Today we are going to read about XGBoost. XGBoost is nothing but gradient boosting, but with some parameters. That's why name is extreme gradient boosting with some extreme parameter. Okay, now let's read this and then do the exercise. The most accurate modeling technique for structured data. Okay, so in this tutorial you will learn how to build and optimize models with gradient boosting. This method dominates many Kaggle competitions and it is considered one of the best traditional machine learning algorithms. Okay. Now, for much of this course, you have made predictions with the random forest method, which achieves better performance than a single decision trees. Random forest, you know, that collection of decision trees and which is most of the times better than a single decision tree. Okay. Now we refer this forest as ensemble method. By definition, ensemble methods combine the predictions for several methods. In case of random forest, there is several trees. Okay. Now we are going to read about another ensemble method, that is gradient boosting. Now gradient boosting is a method that goes through cycles to iteratively add models into an ensemble. It begins by initializing the ensemble with a single model whose predictions can be pretty naive. Even if the predictions are wildly inaccurate, subsequent additions will address those errors. As I said, that first you are taking the first model and here you can expect that errors will be high, but slowly after m2, after m3, after m4, this will get improved. That's what they have stated. Then we start the cycle. First we use the current ensemble to generate predictions for each observation in the dataset. Fine. To make a prediction, we add the predictions from all the models in the ensemble method. These predictions are used to calculate a loss function. Let's say mean squared error. There are many loss function. Just think that you are calculating the square difference of actual value and the predicted values. Okay, then you are taking the mean to calculate the error. Now, then we use the loss function to fit a new model that will be added to the ensemble. Specifically, we determine model parameters so that adding this new model will reduce the loss. The gradient in gradient boosting refers to the fact that we will use gradient descent on the loss function to determine the parameters in this new function. I hope you know what is gradient descent. While studying linear regression, you may have seen this, that you have to find where the error is minimum. Okay, so you have to descend. This is known as gradient descent. Finally, we add the new model to ensemble and repeat. See, naive model, the first one, M1, make predictions, calculate loss, you train the new model, add this new model to the ensemble. Okay. Okay. Now we begin by loading the training and validation data. Let's see the code. Same, pandas imported, train test split, Melbourne housing data set we have worked before also. You have all this data, you have to calculate the price, which is the output, and you have created training set, validation set. Fine. Now in this example you will work with XGBoost library. XGBoost stands for extreme gradient boosting, which is an implementation of gradient boosting with several additional focused on performance and speed. Okay. Now in the next code cell, we import the scikit-learn API for XGBoost. XGBoost.xgb regressor. This is the package. Okay. Now this allows us to build and fit a model as we just did in scikit-learn. Same way, you just have to create an object of this particular class. Then you can use fitting. It will train your model. Okay. Now you have to predict the model and you have to evaluate the model. So you are calculating the mean absolute error. Now parameter is the main important thing. That is the main difference between gradient boosting and extreme gradient boosting. That is parameters. Here as we are using many models together, so automatically it was becoming comparatively slow. So to improve that performance and the accuracy, we have adjusted the parameter. It is not a different model. Okay, please remember this. Gradient boosting and extreme gradient boosting, the main difference is in parameter, so that performance and accuracy can be improved. Now the first parameter, number of estimators. This specifies how many times to go through the modeling cycle described above. It is equal to the number of models that we include in the ensemble. Too low a value, underfitting, which leads to inaccurate predictions. You know what is underfitting? That means it is unable to predict in training data and testing data. Nowhere, never. So you never want underfitting. Now, but if you use number of estimators high, then what will happen? Then it will be overfitting. Then it will try to remember all the points. So that is also fine for training data, but not for testing data, right? Because in training data it has seen all the data, so it will predict you uh, almost correct everything. But in case of testing data where it has not seen the data, it will not be able to correctly predict. too high a value causes overfitting, that also we know. So you have to keep the values typically between 100 to 1000. Okay, though it depends a lot, and here they have taken 500. So they are training the model. Fine, let's see the output. This is the output. Okay, now the next one is early stopping. Now see, number of estimators, you can fit 500, 1000, 1500. There can be many numbers. So you are using one more parameter that is known as early stopping, that is used to reduce the overfitting. How? After every iteration, it will check whether the score, the performance score, is getting improved or not. If it is not getting improved, then stop the training. That is what is done by early fitting. So what you can do, you can keep this high, you can use early stopping, and you check after each iteration, and then you can stop it before it reaches the number given by you. Okay, you understand? Let me read this. It offers a way to automatically find the ideal value. So early stopping causes the model to stop iterating when the validation score stops improving. Whenever you see that score is not getting improved anymore, okay, then stop the training. Even if we are not at hard stop or in estimators. Okay, that's what I have stated you. Maybe you have not reached 500. Maybe in 300 it is finding that score is not improving anymore. So early stopping will stop the training. Okay. So it is smart to set a high value for number of estimators. You set it high, but let the early stopping decide whether to continue till the number you have given or to stop before that, so that the model so that it doesn't get overfit. Okay, so then use early stopping rounds to find the optimal time to stop iterating. Now, since random chances sometimes causes a single round where validation scores don't improve, you need to specify a number for how many rounds of straight deterioration to allow before stopping. Sometimes it may happen that after a single round it is not improving. After a single round it is not improving again. So in case of early stopping, we'll stop that. So don't let that do it. Okay, maybe after 3 or 4 times it may again improve. So you just set a parameter. Okay, check 5 times. If it is performing poor for 5 times, then only stop. Okay, it is like giving a chance to a person to appear in his or her exam more than once, so that we can decide whether he is passed or failed. Okay, not in the first exam, but let him appear in the second time, the third time, then decide whether there is a chance of improvement or not. It's like that. Give them 5 times chances. If after 5 rounds also it is not getting improved, then stop it. Okay, or it may happen that it has started improving again. Okay, so that is what they have said. Early stopping rounds. You also need to set aside some data for calculating the validation scores, that you know, that which is done by eval underscore set parameter. This keeps some data aside so that you can calculate the validation score. Now see how to implement this early stopping. Here we have trained this model, so we are just using the parameters. See, XGB regressor, you have created the object, number of estimators 500. Now while fitting, you are passing the training data set. While training, now early stopping round is 5. Okay, so tolerate up to 5 rounds, right? If even after 5 rounds it is not improving, stop the modeling. Else, let it train. Okay. Now evaluation set, this X validation data set, Y validation data set, where you will do the validation. Okay, separate data set. Okay. Now verbose equals to false. If you want to feed a model with all of your data, set n estimators to whatever value you found to be optimal when run with early stopping. Okay, learning rate. Now, instead of getting predictions by simply adding up the predictions for each model, we can multiply the predictions from each model by a small number before adding them in. This means each tree we add to ensemble helps us less. So we can set a higher value for number of estimators without overfitting. If we use early stopping, the appropriate number of trees will be determined automatically. So in general, a small learning rate and a large number of estimators will yield more accurate models, right? Though it will also make the model longer to train since it does more iteration through the cycle. This is the default learning rate. Okay. Now, if you want, you can specify. If you don't, it will be default. Now, number of jobs parameter. So on larger dataset where runtime is a consideration, you can use parallelism to build your models faster. So it's common to set the number of jobs parameter to the number of cores in your machine. On smaller dataset, you don't need to do this. But in case of larger dataset, you can set the number of jobs, but that depends on which configuration you do have. Okay. So what will happen? You can introduce a little bit of parallelism. So your model gets trained faster, because that is what is the disadvantage of boosting method, right? You have to wait. After M1 gives you the output, then only you can send it to M2. After M2 gives, then you can send it to M3, right? So you have a problem. That is why boosting is a bit slow in comparison with bagging. That problem is solved by XGBoost, right? By using this number of jobs, so that some amount of parallelism can done. This will make your models faster. See, number of jobs equal to 4. But your machine should have good configuration for this. Now, XGBoost is a leading software library for working with standard tabular data, the type of data you store in pandas data frame, as opposed to more exotic types of data like images and videos. So with careful parameter tuning, you can train highly accurate models. Okay, now let's do the exercise. Okay, so the parameters we have learned: number of estimators, number of jobs, learning rate, and uh, early stopping round. Okay, now let's do the exercise. In this exercise, you will use your new knowledge to train a model with gradient boosting. This is the setup, and you are doing train test split. Okay, so build model. From XGBoost, you have to import XGB regressor. Okay. Now, in this step, you will build and train your first model with gradient boosting. Okay. So, begin by setting my model 1 to an XGBoost model. Use the XGB regressor class and set the random seed to 0. Okay. So, you just have to call this my model 1 calls to this one, and random state equal to 0. Okay. I think you know what is random state. We have discussed many times before. Now you have to feed the model. Okay. So same way, my underscore model underscore 1 dot feed. You have to pass x train and y train. These are the training data set. Sorry. Okay. Now let me run this. Fine. Now set predictions underscore 1 to the model's predictions. You have to predict. Okay. So my underscore model underscore 1 dot predict. You have to predict on validation data. Okay, so let's run this. Fine. Now finally use mean absolute error to calculate the MAE corresponding to the predictions for the validation data set. Validation data are stored in y valid. Okay, so mean absolute error function, and you have to pass our output predicted by model, and what is the real output, that is in y valid, right? Okay, now improve the model. Now that you have trained a default model as baseline, now you are going to tinker with the parameters, which is the main thing of the XGBoost regressor. So again they are telling you to begin by setting my model 2 using an XGB regressor class, and use what you have learned. Use default parameters, number of estimators, learning rate to get better results. Okay, so you have to train a second model with parameters. So we can write XGB regressor. See, what are the parameters? Number of estimators. So give number of estimators as number of estimators as, let's give 500. Okay, now you have to give learning rate. So learning rate equals to, you can give anything, 0.05, by default 0.01. Okay, So anything else? Then feed the model. Okay, then feed the model. Dot feed. Same way, you just have to feed the model x train, y train. So x train, y train. Okay, fine. Next, set predictions to model prediction. Okay, same way. The model will predict x valid. Fine. Okay. Next, use MAE to calculate the mean. What are the things we have done before? We are doing same. Mean, absolute error, and we are passing the predictions done by model and our y valid. Okay, so fine, let's run this. Okay, mean absolute error. Okay, now let's break the model. In this step, you will create a model that performs worse than the original model in step 1. This will help you to develop your intuition for how to set parameters. You might even find that you accidentally get better performance, which is ultimately a nice problem and a valuable experience. You can print this. So if you just run this, let's see. This is the MA, but here let's check this MA. Oh, sorry. See, 18161. Now this is 17101. Okay, so they have stated, okay, they expected that you will perform worse, but you might find that better performance. For us, it's better performance. So it's a nice problem to have and valuable experience. Okay, now they are telling you to set model 3 to an XGB model using XGB regressor. Okay, so let's do it once again. XGB regressor, and you have to set any random set, and they are telling you to change the default parameters, number of estimators, and learning rate to get high MA. Okay, high MA, that's okay, no problem. How can we do this? Change it to 200. Learning rate, uh, change it to 0.08. Let's do the experiments. Feed the model using X train, Y train predictions, all the things. Let's copy now. So this is fit. Here we are going to fit the model. This will be 3. We are going to do the predictions. So right, okay, sorry, to make it 3 you have to make it 3. Now for MAE, here also it will be predictions 3, MAE 3, and sorry, MAE underscore 3. Let's uncomment this and check. Okay. Okay, sorry. You must specify the parameters in my model 3 so that it attains higher MAE than model 1. Okay, what should I give so that it performs worse? 17,000, but it is performing better. Okay, let's say what it will provide if I give 100. Let's see, is it performing better or still not? Okay, let's give it 10, then obviously it will perform more. See, now it is performing so poor. Let's do one thing, change this, give it to 0.1. Now it is improving again. Okay, so you understand, this way you can change these things and give. Okay, number of estimators naturally should be higher because you are training multiple times. Okay, so these things you can do, or you can use these methods also, like early stopping. You can use them also. They have not given in exercise, but try to apply this early stopping round also, right? And play with this. You can use number of jobs also, but depending on your configuration, so you think before you try on this one. And if you want to try, you have good configuration, then you can play with this one. And that time I will suggest you to note down the timing, like first take a time in a particular variable, then after training the model you again calculate the time, subtract them, then calculate how much it is taking. Okay, so you can check how much your speed is improving. If you want, you can play with these things. Okay, so now next thing is data leakage, that we are going to understand in our next class. So meet in our next class. Till then, bye, happy learning.